Okay, so I'm just going to run through some tests to demonstrate that the system works correctly. So first off, let me just say that these two LEDs are for the left and the right motor PWM signal sent to the motor shield. This simulates the sense current output pins for A and B for the motor shield, direction pins for the left and right motor for the motor shield, and brake, left brake and right brake pins. And then for the buttons, this is the left motor increase and decrease, right motor increase and decrease. That's the diagnostic mode here, and then the brakes are here. So I'll just reset the system to back to initial state. I'm going to clear this. And so what we want to see is the zeroed kinematic information being sent every second. So as you can see, it's every second, give or take a few milliseconds. To verify that through the oscilloscope, that's just connected to the transmit transmit pin. And so yeah, the system works correctly with the initial state. The second test will be for a left motor and right motor increase button press, extended press, so longer than the debounce time. So there we go, I've pressed it once. You can see that the PWM increases. The linear velocity of the left motor increases in the forwards direction, and the orientation and position update over time. I'm going to do the same for the right motor increase, I think it's that one. And you can see that's also increased. So they've increased by 20% of the maximum velocity in the forwards direction. And I'll just press one of them again, the left motor increase again, to show you that it sends a message not only when the at a 1 Hz rate, but also as soon as the button has been debounced. And these, I'll press one of them all the way so it goes up to 1 in the forwards direction, and then I'll do the same for the left and right motor decrease. So this is me pressing the left motor decrease. You see it decreases by 20%, and same thing here for the right motor, 20%, and the kinematic information updates over time as expected. And the motors, and so the direction pins are 0, indicating forwards. If I press this long enough, we'll start being in negative velocities, and you can see that the PWM increases. You can see here the PWM increases both in the forwards and the backwards direction, and that's just indicated here. And so same thing for the right motor velocity decrease. It goes all the way over here, and you'll also see that when both motors are above a cutoff point in either the forwards or the backwards or one of the two directions, we get this warning light. Let me see if I can measure I'll show the frequency with my oscilloscope. There we go. And so you can count effectively 12 toggles. That lasts 3 seconds. So that's a 4 Hz rate toggle for that LED. That's only, I'll just show you, just to show you, you can see the PWM decreasing and increasing as I go to the other, like left motor forwards and right motor backwards, and same thing, we'll still see this. So just to note here, the left and right motors, the left motor is full speed forwards, right motor is full speed backwards, and so we see both PWM, both PWMs for each motor at full duty cycle, but the right motor direction pin is on, signifying backwards, and left motor direction pin is off, signifying a forwards direction. Since both motors are above the cutoff frequency, we still get this warning light, and that's disabled in diagnostic mode. So let me just press the diagnostic mode button now. you'll see that that turns off. And now we start getting another thing that the diagnostic mode does is prints the current information, maximum sensed current information since the last diagnostic mode and since the and over a 2-second period. And so what I'm going to do here is simulate using this potentiometer. So I'm going to turn this potentiometer and you'll see these values changing. So there we go. Okay, so next we're going to test the brakes. As soon as the brakes are pressed, we should see the brake lights turn on, the motor velocities being reset to 0 both on the terminal and through the PWM. So I'm just going to do that. So I press the brakes, the lights turn on, you see a message signifying that the brakes have been turned on, the velocities are reset to 0, and as soon as I let go, you see that brake off message, the lights are off, and the motor's velocities continue. The PWMs stay at 0. So the last task that I want to show working is the sensor processing task, which periodically every 20 milliseconds effectively busy waits for 5 milliseconds. I've got an LED hooked up to it just to demonstrate that. And this is a PWM that this effectively generates. So it's busy waiting for 5 milliseconds, and then the rest of the time is just the system is free to do other stuff. Now, unfortunately, I've not been efficient enough, I don't think, because I need to comment out some task. I just picked this one arbitrarily for this final task to run. If I upload it again with all tasks on, everything but this works. My guess is that this is just too frequent a task, and so that all of the context switching that scheduler has to do means that this gets starved of CPU time, and as you can see the LED isn't on, nothing's blinking. But on the plus side, I'll just mash some buttons kind of to demonstrate that everything else works perfectly. Just as a kind of a consolation, that was the brakes on and off, the diagnostic mode, and I'll just put it up to some maximum velocity. Make sure the diagnostic mode's off. That's still blinking. So everything works but that. My best guess as to how to fix this would be, I guess, to be more efficient. I'm not exactly sure how floats are handled in AVR assembly, but maybe reducing floating point operations could save some clock cycles, and just in general being a bit more optimal. But I haven't managed to do that.